Okay, let's dive into something that is fundamentally transforming global infrastructure.
Hmm.
Today, we are taking a deep dive into the constraints that are pushing the frontier of advanced computing. Well, right out of our atmosphere entirely.
That's right.
The core idea here is this. Advanced AI is hitting a massive physical wall right here on Earth,
Yeah.
and it's driven by the need for two resources we sort of thought were infinite: energy and water.
Exactly. We've synthesized a really comprehensive set of sources, all updated right through November 2025, and they detail the economic necessity, the sheer technological readiness for this massive shift.
Okay.
So for you, the listener, our mission is to understand the structural limits on Earth that are making space-based AI and, crucially, the power to run it. Not just some far future possibility,
Right.
but the definitive trajectory for the next 10, maybe 20 years. We're watching a real-time exodus.
So let's unpack that. Let's start with the scale of the energy crisis, because the speed of the demand acceleration is it's mind-boggling.
It really is.
Worldwide data center electricity use is projected to more than double in just 5 years.
Just 5 years, yeah. Rocketing from 448 terawatt hours in 2025 to nearly 1,000. Well, 980 TWh to be precise, by 2030.
And that doubling, that's really an AI effect, isn't it? If you zoom in on the specific demand from dedicated AI clusters.
It's even more extreme. The consumption there is projected to increase almost fivefold.
Fivefold, wow.
Yeah, from 93 terawatt hours this year to 432 in 2030. I mean, when the global energy demand of AI alone hits 200 terawatt hours, which it did in 2025, that's more than the entire annual electricity consumption of a country like Belgium.
And that's just the starting line.
That's the starting line.
Which was an immediate, and I mean severe, strain on local grids. We saw the percentage of national electricity used by U.S. data centers just jump from under 2% a few years ago to 4.4% in 2023.
Mm-hmm.
And the forecasts suggest we could hit 6.7%, maybe even 12% by 2028.
And in terms of gigawatts, total U.S. data center demand is expected to more than double in the next decade, from 35 gigawatts to 78.
This is where those structural limits really hit.
This is exactly it. We call this the infrastructure bottleneck. The constraint is it's no longer just about how much capital Microsoft or Amazon can deploy.
It's physical.
It's physical. Permitting delays for new transmission lines, decade-long backlogs for critical components like large transformers, and just sheer utility capacity.
The sources gave a pretty chilling example of this right in the heart of, cloud computing.
Absolutely. Northern Virginia, it's home to the world's densest concentration of data centers, and they had to formally pause all new service requests until 2026.
Why?
Because the local utility simply couldn't guarantee grid stability if they connected any more of these massive facilities. The systems are literally capped out.
That's a huge economic hurdle, and it's happening right now.
Right now.
So energy is one hard limit.
Yeah.
But the other one, the one that's equally fundamental, is water. And this is the part of the story most people miss when they think about the cloud.
They do. Because data centers rely so heavily on evaporative cooling, this process uses the highly efficient physics of evaporation to dissipate heat.
Local water's gone.
The trade-off is that the water is consumed. It turns to steam, and it doesn't cycle back into the local water table.
And the scale of that consumption it's astounding.
Mm.
A typical 100 to 200 megawatt hyperscale facility needs between 10 and 20 million liters of fresh water.
Yeah.
Every single day.
Which is the daily municipal consumption for a small city of 100,000 people.
A whole city's worth of water.
If you look at the physics, for every megawatt of waste heat you need to reject, you're evaporating about 0.4 to 0.6 liters of water every second.
Okay.
Now scale that to the future. A 1 gigawatt AI data center, it will consume 35 to 50 million liters of water daily. You're basically creating a small, localized drought risk with every new cluster you build.
Which is why we're seeing places like Arizona and Texas proposing these strict disclosure mandates.
Right. And it's not just the desert Southwest. Even in Europe, Ireland now sees data centers eating up 21% of the national electricity.
21%.
And the Netherlands is putting formal limits on any new construction. The analysis confirms it. Earth is simply running out of cheap, accessible power and cheap, accessible cooling all at the same time.
So we know the limits on Earth are hard. Before we look up, we have to talk about the massive stopgap solution that's powering this whole transition.
Right.
The rise of small modular reactors, or SMRs, as the transitional backbone.
And what's fascinating here is the strategic response from the hyperscalers themselves. They've recognized the energy bottleneck is the definitive constraint on their growth.
So they're taking matters into their own hands.
They've shifted from being passive consumers to becoming vertically integrated energy producers. They are building their own private utilities.
And the money they're committing reflects this. Microsoft is pouring $80 billion into AI infrastructure with a huge focus on energy sovereignty.
Amazon Web Services, $86 billion. And Alphabet, or Google, they've allocated $75 billion globally, and they're specifically targeting nuclear and next-gen energy partnerships.
SMRs seem to be the logical choice for this transition.
They are. They offer carbon-free, dispatchable baseload power.
Right, so it's always on, not like wind or solar.
Exactly. It's always on. And it's without the massive regulatory hurdles or the huge cooling footprint you get with the traditional multi-gigawatt plants.
And this isn't just hypothetical anymore. By November 2025, we saw major commitments.
We did. Google partnered with Kairos Power to secure 500 megawatts of SMR capacity before 2030. AWS invested $700 million in X-Energy.
And Microsoft's strategy includes acquiring output from facilities like the revived 3 Mile Island. This is a corporate race for private constant power.
It is. The technical advantage of SMRs is that they're designed to be, factory manufactured. Under ideal conditions, this promises construction timelines of maybe 24 to 36 months.
Which would let companies deploy these configurable reactor farms right next to their data centers.
That's the idea.
But here's the friction point we found in the source material. The SMR reality check. The timeline might not be fast enough, and the economics are just exploding.
They are.
Projected capital costs for early U.S. SMRs have hit $14,600 per kilowatt. That's 5 times the initial 2020 projection.
Mm-hmm.
Doesn't that risk derailing the whole bridge strategy?
It creates a massive financial hurdle, absolutely. When your bridge technology costs 5 times what you budgeted, it forces you to look at the next option even faster. And on top of that, there's a supply chain bottleneck.
For the fuel.
For the fuel. SMRs rely on specific next-gen uranium fuel, like HLEU. And right now, China heavily dominates the refining and processing capacity for that critical fuel.
So SMRs are essential. They're the critical bridge we need from, roughly 2030 to 2040.
That's the window, yeah. But the 7 to 10-year timeline for these first-of-a-kind deployments means they simply may not scale quickly enough to absorb that ferocious AI surge in the early 2030s.
And that inadequacy drives the focus squarely upward.
To Section 3. The orbital horizon.
This is where the analysis paints space-based solar as the inevitable answer. So let's dig into the physics. Why is geostationary orbit so much better than anything we can do down here?
It's pure, beautiful physics. In geostationary orbit, you're above the atmosphere. You get the full solar constant 1,360 watts per square meter.
No clouds.
No clouds. And more critically, due to orbital mechanics, a GEO satellite is only in Earth's shadow for 1% of the year. It's illuminated 99% of the time.
Which means continuous baseload power.
Continuous. That's a radical contrast with terrestrial solar, where you have atmospheric losses, the day-night cycle, that reduces your peak irradiance by 25 to 30%.
So on Earth, even in sunny places, solar farm capacity factors, the actual power you get over time, are only, 20 to 25%?
Yeah, in space, that capacity factor is between 70 and 99%. That translates to a practical productivity advantage of 6 to 8 times over land-based panels.
And financially, that's huge.
Oh, it's massive. It means you need dramatically fewer, or maybe even 0 batteries.
Yeah.
That fundamentally transforms the entire energy distribution model.
And the other key enabler that makes this plausible now, and not in 2070, is the launch cost revolution. Space stuff used to be science fiction because it was just so expensive.
Correct. The Falcon 9 has already crushed average launch costs to about $2,600 to $3,000 per kilogram to low Earth orbit. That's a 10-fold decline.
And Starship. If Starship reaches its projected goal of $200 to $500 per kilogram,
Yeah.
Even if it's at the high end of that.
That makes the wide-scale deployment of multi-kilometer solar arrays economically plausible. Launch cost reduction is the single biggest multiplier here.
And this transition isn't waiting. We've moved from just a concept to actual operational hardware.
We have. Caltech's SSPD-1 successfully demonstrated its microwave array for power transfer low-orbit experiment, they call it MAPLE, between 2023 and 2025.
And that achieved the first in-space coherent microwave power beaming back to Earth. It actually works.
It works. And the international competition is heating up fast. China has a strategic push for a megawatt demonstrator by 2030 and a gigawatt station by 2045 or 2050.
The European Space Agency is in on it too with their Solaris program.
Right. And that infrastructure isn't just for power, it's for compute itself. Orbital data centers are here. StarCloud is the pioneer.
Their StarCloud 1 satellite launched in November 2025. That's the first time a massive AI chip, an NVIDIA H100 GPU, has been put into outer space.
They're testing everything, radiation shielding, thermal pathways. They are running large transformer models in orbit right now. Their long-term vision is an orbital AI compute complex of 5 gigawatts.
And the traditional hyperscalers are following right behind. Google's Project Suncatcher is looking at a distributed constellation using their own TPUs.
With prototypes expected as early as 2027, but this isn't just about moving the cloud, it's about solving immediate data bottlenecks.
You mean on-orbit pre-processing?
That's the critical immediate use case. Think about a satellite with synthetic aperture radar. It can generate 10 gigabytes of raw imagery per second.
Which is prohibitively expensive and slow to downlink.
Exactly, but with orbital AI, those systems can detect objects, classify them, and just send down the distilled insights. It reduces bandwidth costs by orders of magnitude and allows for real-time disaster response. That's the immediate ROI.
So power source is solved, compute is moving up, but space isn't a silver bullet. Section 4 is about the unique physical constraints up there, which are way harder than the problems on Earth. We had to talk about the thermal management hurdle.
That's right. On Earth, we use convection and conduction air and water to carry heat away. In the vacuum of space, you have none of that.
So waste heat has to be rejected entirely through radiation.
And the physics governing this is the Stefan Boltzmann law, where your radiative power scales with the absolute temperature raised to the fourth power, T to the 4.
So what does that T to the 4th dependence mean in plain English?
It means we are looking for every single degree of temperature increase we can possibly manage on our components. A tiny change in operating temperature gives us massive, exponential savings in the radiator size and mass we need.
Let's quantify that challenge. A 1 gigawatt orbital data center has to reject about 600 megawatts of waste heat.
Right.
If we try to run components at normal Earth temperature, say 40 degrees Celsius, you'd need over 100,000 square meters of radiator area. That's a facility almost 321 meters on a side. It's huge.
But, and here's the key, if you can raise that operating temperature significantly by using high-temp electronics like silicon carbide or gallium nitride chips, the reduction is spectacular. Doubling the temperature can shrink the required radiator area by a factor of 40.
Wow.
That is why high-temperature electronics is a core multi-billion-dollar technology driver for space AI.
And the cooling solutions are incredible. Things like droplet radiators, which use liquid metal droplets to radiate heat.
Or two-phase cooling systems. Basically, advanced heat pipes that move heat thousands of times more efficiently than solid copper.
But that internal physics hurdle is matched by the biggest external threat, the environmental constraint of the Kessler syndrome.
The runaway debris cascade, where collisions generate debris faster than natural drag can clean it out of orbit, potentially sealing us off.
And the crisis is accelerating in real time. The sources noted that SpaceX's Starlink satellites executed 144,404 collision avoidance maneuvers in just the first half of 2025.
Which is triple the pace of the previous 6 months. This isn't a future problem, it's a current maintenance nightmare.
And the modeling shows that the crucial 520 to 1,000 kilometer band is near, or maybe already at, the threshold where this could become self-sustaining.
It's an existential threat to the whole industry. A single catastrophic impact with one of these multi-ton solar arrays could create tens of thousands of fragments, risking the feasibility of all megastructures in LEO.
So we have this dual-track energy strategy emerging. SMRs are the critical near-term backbone, filling the gap from 2030 to 2040.
And then space infrastructure, SBSP, and orbital data centers, that's the ultimate platform, taking over from 2040 to 2060.
But the transition itself creates this immense governance challenge.
One we have to address now: launch systems, space-qualified hardware. This stuff requires investments in the hundreds of billions. Only major corporations and national governments can afford it.
Which concentrates digital power and just blows up the global digital divide.
Absolutely. The countries that can afford to play in space will secure an exponential lead in AI capability.
And the legal questions are immediate and so complex. Data jurisdiction, whose laws apply to a server orbiting 400 kilometers above the planet.
And spectrum allocation. These massive power beaming and communication systems risk crowding key frequency bands we need for everything else. Who allocates that finite resource?
On the positive side, The economic transformation is huge.
Yeah.
I mean, we are looking at a potential 10 to 25% global GDP increase by 2050 from this,
But that speed introduces severe societal risks, mainly automation displacement. Estimates suggest 40 to 60% of occupations face partial automation.
which is driving these serious conversations around post-scarcity economic models,
Yeah.
like AI-funded universal basic income.
Hmm.
So the transition feels inevitable because of the constraints on Earth and the tech readiness. We're in phase I now, the demonstration phase, from 2025 to 2030.
And we are accelerating very quickly toward phase 2, which is gigawatt scale deployment from 2030 to 2036. The key takeaway is simple. The constraint on humanity's technological leap isn't physics or money anymore.
It's the speed of our governance.
Exactly.
So we'll leave you with this final provocative thought based on that timeline. The space AI transition is moving humanity toward a post-scarcity economy, maybe even a first step toward a Type I civilization on the Kardashev scale. But this whole journey is constrained by the speed of global governance.
Hmm.
If space debris keeps accelerating and the legal vacuum persists, are we headed toward a crisis response scenario where we only govern space after a catastrophic failure? Or can proactive international governance ensure equitable access and environmental protection before those critical low Earth orbits become unusable?
Something to chew on.
Something to chew on as you consider where the next decade of AI development will truly be located.